So just to recap, at this point we are pretty good at figuring out the F and T matrices for any combination of translations or a single rotation about the X or Y or Z axis. And what do we want to do? Well, we want to figure out what is the frame transform and therefore the homogeneous transform that transforms a single fixed point between different coordinate frames, so we know what its location is in different coordinate frames for any arbitrary sequence of rotations and translations. There are, in fact, two different ways to compute the relationship between two frames. One of them is using the moving axes approach. The other is the fixed axes approach. Both approaches are good. It is useful to be able to do both. Some are easier with moving, some are easier with fixed axes. If you can do both, then you can try it both ways and check your results. But for now, we are just going to take a look at the moving axes approach, and later we may get to the fixed axes approach. So here's a problem that we had before. And we have the W frame and the G coordinate frame, and I want to know, how do I compute the frame transform from W to G? That is, how do I move starting at the W frame and move it so that it aligns with the G frame? And I strongly encourage you to do this using some pencils that are stuck together with some duct tape or something. Physically make these frames and see if you can figure out what is the transformation. So there's a lot of different ways that you can do this. I am just going to show you one approach. I think that I was using W as world and G as gripper, so we're going to start with our world coordinate frame. There's our world coordinate frame. So here's our world coordinate frame down here, just so you remember where we're trying to get to. I'm going to leave this picture up in the top right corner. And what I'm going to suggest is the first thing we should do is we should do a rotation about the world X axis by -90 degrees. And so here you have the new frame that I get after I do that. I'm going to call the original frame was the world coordinates. I'm going to call the intermediate frame, the new frame that we just got, sort of the one coordinate frame. It has axes x1, y1, and z1, right? And so after rotating, this is, of course, -90 degrees, because if I take my right hand and I stick my thumb, oops, come on, let me draw. And I stick my thumb along the x-axis, then my fingers are going to curl. Ooh, my fingers are looking great today. My fingers are going to curl in that direction, which means that this way is -90, because that's in the other direction from the way my fingers curled. So here is the one coordinate frame after I, just by itself, so that you don't see the world coordinate frame isn't confusing you. All right. And now what I want to do, remember, my ultimate goal is I'm trying to get to align with this coordinate frame. So at this point, if you look, the z-axis of the one frame is aligned with the z-axis of the gripper frame, but the x and y are still out of alignment. And so what I'm going to suggest we do now is we do a rotation about the z1 axis, so that we sort of flip that x-axis up and the y-axis over. And again, if you look at this rotation, we are rotating about the z-axis. If I take my right hand and I point my thumb that way along the z-axis, then my lovely fingers are sort of curling over this way, but we want to rotate the other way, so that means we're rotating by -90 again. And so we're going to call this new axis the 2 axis, because it's sort of our second frame 2. It's our second intermediate point. And here's a picture of frame 2 by itself. And remember that we started with the world coordinates, right? We've been doing rotations, but we haven't done any translation yet. So our origin of the 2 frame is still exactly here, and we need to move over there. Of course, we're not going to move in the y direction, right? We have to move in the z direction now because we're talking about frame 2. So we need to translate by 0, 0, 5 relative to coordinate frame 2. And here we're doing our movement, and that puts us over into what the gripper frame looks like. So some things to note about the approach that we took. Every step along the way was based on the resulting frame from the previous step. So it's very important to notice that when I said I'm going to do rotation 2, I was using the axes from frame 1. I wasn't using world axes, right? And similarly, when I moved from 2 to the gripper frame, I was looking at the direction of the axes in 2's frame where z was pointing. Right? In 2, z was pointing in this direction, whereas if you look at where we started with the world, that was the y-axis, right? So you can rewind and look at that again. But the most important thing here, every step along the way is based on the resulting frame from the previous step. So if you go back and see what we did, we first did a rotation about x of negative 90 degrees. Then we did a rotation about the z-axis of negative 90 degrees, and that was the new z-axis after we'd done this rotation. And finally, we took our intermediate frame 2, and using that as our reference frame, we translated by 0 in the x direction, 0 in the y direction, and 5 in the z direction. And again, that was in the intermediate frame 2's z direction. So once we have these moves, it's actually pretty easy to get the matrix. Again, I think I said this when I introduced these equations before. You don't need to memorize these equations. If I were to give you a test with these, I would give you a copy, but you should be comfortable using them. So here are all of the transformation equations, right? We started for the rotations with just z, but then we got x, y, and z, and this is the translation. And so to build up the matrix that represents that frame transformation, or the it's complementary, I guess you would call it, homogeneous transformation, big T transformation, what you do is you take your moves that you've summarized in the order that you did them, 1, 2, 3, and the first thing you do is you list those moves from left to right. So here you go, I've just copied these from up to down and put them in left to right order. And now we're going to use that chart of matrices, and if you're in my class, I've also uploaded that to the class website. We're going to replace each move with the appropriate matrix. So here's the chart again, a little bit small, but you can still read it, I hope. And I figured out that rotate x negative 90 actually corresponds to this matrix. Rotate z negative 90 corresponds to this matrix, right? Because I just took rotate z of theta, plugged in negative 90 degrees for all this stuff. Translate 005 is just this 005 with the unit matrix on the outside, or on the top left, 3 by 3. So now I just have to do matrix multiplication to multiply these together. And when I do that, I get this matrix. And of course, this matrix represents either how I transform a frame from world to gripper coordinates, or, probably more useful for me, if I have a point somewhere in space and I know the location of that point in gripper coordinates, I can tell you the location of that point in world coordinates. Okay, so let's just do a couple of sanity checks using Mathematica to plug in some numbers and see what happens. Okay, I have a couple of Mathematica files that I have made that help me out here. I've already opened up Mathematica, obviously. And the first one I have is I defined all of my 4x4 matrix operators in a file. I have shared with you a PDF of this file, but I'm not giving you the original file because I think it's good for you to type this stuff in yourself. It helps you get used to Mathematica. In any event, I'm going to evaluate this notebook so that all of these functions are defined. And then I also have another notebook that I've made where I just define a function called myPoint, so I can quickly make up a 4x1, right, 4 rows, 1 column vector for points, and then I define a few points like the origin and whatnot. So I'm going to evaluate this notebook too, just so I have these functions all built in. And now I'm going to open up a new notebook so that we can do the work that we're doing right now. And I'm going to try and magnify the window a little bit so you can see it a little bit bigger. So what I'm going to do is we said that our t from g to w is this equation. Let's just make sure that actually works. If I say I want to know what t, let's define a new function called tgw. That magnification doesn't really seem very big. Let's try 300%. There we go. So I'm going to say that tgw is going to be rot x, right? I have my rot x function, and I want to do 90, but of course I have to say pi over 2 if I'm in Mathematica. Matrix multiply that by rot z of, ooh, that was negative pi over 2, right? Negative pi over 2. Here, I can pull this a little bit wider. Matrix multiplied by rot z of negative pi over 2, matrix multiplied by trans of 0, 0, 5, and I'm going to shift enter, and there's my answer, and I'm going to say display as a matrix, which I can either say display as matrix here, or I could have just typed matrix form TGW, but look at that. I look at what I've got over here. I look at what I've got over here. They look pretty much the same, so that's pretty good. So I already have that point called origin, right? 0, 0, 0, 1. So theoretically, let's just look at this picture on the slide for a minute. If the origin of G is at 0, 0, 0 in G coordinates, I expect it to be at, let's see, 0 for the x and positive 5 along the y and 0 for the z. So that's kind of what I'm looking for. And so let's try and multiply it out here. So let's call this, I don't know, G origin in W coords is going to equal TGW dotted with my origin, and I'll enter, and that tells me that if I do a matrix form of G origin in W coordinates, and I hit enter, I get 0, 5, 0, 1, which is exactly what we said we should expect. Unfortunately, this isn't looking as good as it did, but right, but so 0 on the x, 5 in there, and 0 on the z. So that's good. So far so good. Let's look at another point. What about the origin of the w axis, right? I want to know about the origin of the w axis, which is at 0, 0, 0 in w, but 0, 0, negative 5, I figured out. 0, 0, negative 5 in G coordinates. So if we make a new point, so let's see if I can do this. So my make point function I called my point, right? So let's make a new, oh dear, you can't see that. There we go. Let's make a new point. We'll call it W origin. Oh, I see. I can move over a little bit there. Doesn't do diddly squat for me. Okay. W origin is going to be, oops, yeah, my point of 0, 0, negative 5. Right. And if I display that as a matrix, it looks good. Maybe I'll shrink the magnification just a little bit here. Window, magnification, let's do 200%. Hopefully you can still see that. Okay, so that was W origin, and I want to take my TGW. So let's see, what is the origin of W in W chords? is going to be my TGW, matrix multiplied by W origin, because that's the W origin in G chords, and I probably should have called that. And I'll shift enter and check it out. If I display it as a matrix, we find that that is the origin. That looks great. Okay, let's try one more example here. Here I've got a point in G coordinates that I just sort of drew for you. I said go 3 along the y, right? 3 along the y-axis, 4 along the z-axis, and then up 2. So that is the point 2, 3, 4 in G coordinates. And if we think about that, where do we expect that to be in W coordinates? It's still going to be 2 up, but that's going to be the z-axis now, right? And it's going to be 5 over plus the additional 4 over, and forward wise it'll be the same distance here, so it will be 3. Let's let Mathematica do the math, and then we can sanity check that it's right. So for Mathematica, I'm going to say my new point is going to be, I'm going to use my point function to make a new point at 2, 3, 4. So let's say new point in G is, right, because it's in G coordinates, so my new point in G coordinates is the point 2, 3, 4. And I'm going to say new point in W chords is going to be the transformation from G to W multiplied by my new point in G. Matrix multiplication, right? So it's just a dot, and I hit shift enter, and I get this 3921, and just for fun, let's display it as a matrix, and then let's see. So it's saying that this point is 3 in the x direction. Well, it's 3 in this direction, which would be in the y direction here, which is 3, so good, so that's right. And it is 9 in the y direction, so it's 9 this way, which is 5 plus the additional 4 that we were in the z direction, so 5 and 4 is 9, good. And the height is 2 in the z direction, so that all looks super good. Okay, so here's another example. I have the a-axis over here where x points up, y points to the right, and z points into the page. You should use your right hand and just check that when you rotate your fingers from x to y, your thumb points in the z direction. Mine does, if it's your right hand. Similarly, here is my b coordinate axes. And again, I'm going to take my fingers, point them along x so that my palm is in the y direction, and as I curl my fingers towards y, z goes up. And if you look at my picture here, we can figure out, there's, let's see, beyond the rotation difference, we know that here, for example, in A, x is pointing up, and here x is pointing to the left. In B, they're not co-located, their origins are not co-located in the same space. In fact, if we start with frame A and we're trying to move to frame B, it looks like in the x direction, the up-down direction, we need to move 1 unit in the positive x direction. In the y direction, it looks like we need to move 8 units. And in the z direction, this is of course relative to A, we need to move 3 units into the screen. So there are a bunch of solutions to figuring out how to transform the A frame into the B frame. Let's do an example first where we start by doing the translation, and then we'll do the rotation. So I want to figure out the frame transform from A to B, and I said the first thing I'm going to do, so I'm just going to list the movements that I make. Maybe can I shrink this? Well, let me shrink it. Yeah. So I'm going to list the movements that I'm going to make sort of vertically first. So the first thing I want to do is I want to and we said before, it's all positive relative to A, right? So I'm going to translate up by 1, and then over in the Y direction by 8, and then into the screen by 3. So the first thing I'm going to do is I'm going to do a trans of 1 up, 8 to the right, and 3 into the screen. That corresponds to the XYZ. And that's going to take my A frame into some new frame. And that new frame, I wonder if I change colors, if it will let me delete it in a minute. Well, we'll see. That new frame has its origin in the same place as the B frame, but now, let's see. So the X, we'll call this frame 1, the intermediate frame 1. The X1 is sort of the same as the ZB. And the Y1, which is the same as the YA, right, actually goes along here. So there's Y1. And the Z1, of course, is going to also be in the same direction as the ZA. So there's the Z1. Okay. And now I kind of need to look and say, all right, I need to rotate this into alignment with the B axis. And so what I'm going to do is, since the 1X axis aligns with the B's Z axis, I'm going to start by doing a rotation around the 1 frame's X axis. And it looks like I'm going to have to do my rotation. Oh, not enough colors here. I'm going to have to do my rotation sort of this way, right? Because then if I do a rotation, oh, actually, no, you know what? Let's line up so that the y-axes line up, right? So what I want to do is I want to take this one and swoop it around there so it's aligned, because that'll make my life easier. It's always good if you can align one of the axes. So I guess what I'm going to do is I'm going to rotate about the 1 frame's x-axis, and I'm going to rotate in this direction, right, by 90 degrees. And that direction, I'm sticking my thumb up in the air, and I notice that that direction is going to be -90, actually. So the next move I'm going to do is I'm going to say rot x, because I'm going around the 1 frame's x-axis, and I'm going to run by -90 degrees. And after I do that, maybe we'll switch to green. Now that I've rotated by -90 degrees, I've got the y of, we'll call this new frame 2, is aligned there. The x2 is still pointing up, right? But the z of 1 was pointing this way, so now the z of 2 is going to have rotated 2. Because remember, I'm spinning this x-axis. Again, if you get 3 pencils and glue them together, stick them together, something, this will be way easier to see. But imagine that I'm like grabbing the top of the 1 frame and spinning it. Then the y-axis, y2 goes there, and z2 is going to go down here. So let me get my green pen again. And so this is the y1 axis, but it's also the z2. So the frame 2, x points up, y points out of the screen towards us, and z points to the right. And if we look at where we are in this mess, it turns out that y2 is already lined up with yb, right, where we're trying to get to. But the x2 and z2 axes still need to be fixed. Let me see if I can delete some of the mess here. Okay, so now what I want to do is I'm trying to transform from the 2-coordinate frame into the B coordinate frame, and as I said before, where's my pointer? Yeah, it's my pointer. The y-axes are already in alignment, so what I need to do is, if you imagine, if you imagine the 2 frame is all glued together, and I grab this and spin this way, then what I can do is, if I am spinning the y-axis that way, then of the 2 frame, then the z2 frame is going to kind of roll up there, and the x2 frame is going to roll down there, and it should align with the b axis. So if I stick my thumb in the positive direction of y, then that's my right thumb, of course, then my fingers curl like this. I should get better drawing fingers. But that means that we're actually doing a rotation in the positive direction. And again, that's going to be 90 degrees. So we're going to do a rot y of positive 90 degrees. So this is the final solution that we get. We get trans 183, rot x negative 90, and then rot y by 90, by positive 90. So that turns into trans of 183 multiplied by rot x of, we're doing it left to right now, right? Negative 90 multiplied by rot y of 90. So let's just eyeball a few points in here and see what we get, and then we can compare the results in Mathematica. So let's start with our old favorite, the origin. Remember, of course, that we computed how to align the a-axis so that it was, move the a-axis so it was aligned with the b-axis. That was the f from a to b, and that's the same as the transformation, the homogeneous transform from b to a. That's what we computed. So if we start with a point in b, for example, the origin of the b-axis, we should be able to find the location of that same point without moving it relative to the a-axis. So if we look at this, just kind of eyeballing it, how far up is it? Well, the origin is 1 up, so that's x is going to be 1. The y is going to be this 8. And in the z direction, we're going to have 3. So it should just be 183. And now let's pull in Mathematica and try it out. So we said our new, let's see, let's call it our, call it example 2a, right? Because it was our first go at this, was equal to, we did trans of 1 comma 8 comma 3, matrix multiplied by rot x of, well, it was negative 90, but of course that's negative pi over 2, matrix multiplied by rot y of pi over 2, and that gives us this matrix, which if I display it as a matrix, it looks like that. And if we make a, oh, well, I have my origin point, right? I can just take my example 2a and matrix multiply it by the origin, and it tells me it is at, let's display it nice as a matrix so you can say, wow, look, 183 and 183, so that looks pretty good. Here's another point that I just sort of randomly picked. This is 2 along the x-axis, 1 along the y-axis, and 4 up in b coordinates. So in a coordinates, if I just think about it, that should be up. Well, it's up the 1 and then another 4 up, right? So up is 5 in the x direction, and it's not quite as far in the y direction because it was 8 over but 2 back, so that'll be 6. And then in the z direction, again, we used to go 3, but now we're going to go 2. So what did I say? I said 5, 6, 2. So let's just test it out in Mathematica, and let's take my, oh, well, let's make a new point. Sample point is going to be, I'm going to make a point. Remember, this is a function. This my point function is a function that I made. You'll have to recreate it, but my sample point is the point 214. And if I multiply example 2a by my sample point, I get 5621, which is what I expected. So cool. So it looks like example 2a is indeed the matrix that, this matrix here is indeed the matrix that is the transformation, the homogeneous transformation from B to A. Again, I can't be sure, but I'm just kind of sanity checking it. You can do a lot more checks later, but this video is long enough already. Okay, so let's do another solution. This says first we're going to do the rotations and then the translation. I'm going to do this a little bit faster than before. The last time when we did our, after we did our translation, our first rotation was about the x-axis. So let's just do something different. I'm just looking, and what I want to try and do is align some axis. Last time I aligned the y-axis, but I think what I'm going to do, if I spin, yeah, here we go. Look, if I spin A's z-axis, then I can kind of spin it this way and align the x-axis first. So what I'm going to do is I want to rotate this way. And I guess, again, it's by 90 degrees. So after I'm done, I will have the one frame. So, oh, sorry. And that is going to be, if I stick my thumb along the z-axis, then it looks like that's negative 90. So I'm going to do a rot z of negative 90. And that will put me in the one coordinate frame. And in the one coordinate frame, x sub 1 is pointing down, or sorry, to the left, and z is still, so z sub 1, because I rotated the one axis, right? So what I did, I just sort of grabbed this end here and twirled it, right? So this axis stayed put, but so that means that the x-axis went down, and so when I twirled, that means that this y-axis is now pointing up when we're in the one frame. So this arrow here, right, this line here is both x for A, but it's also the y for the one frame, okay? And so now if we look, the one frame has its x-axis aligned with the B's x-axis, and so the x-axes are aligned, but the y-axis and the z-axis are still not aligned. So again, remember, this is exactly the same problem we did before. What am I doing now? I'm just trying to do the multiplications a different way, imagining I figured it out a different way and seeing if I get the same result. So let's see. So now I have the one frame, and I have to align everything for the B frame with the B frame. So I guess maybe since my x is already aligned, I'm going to sort of spin this. And what do I want to do? I want to spin it this way, right? So that the y, instead of pointing up, points forwards. So again, if I'm spinning this way, if I do the whole thumb trick, that looks like that's a negative 90. So that means that we're going to do a rot around the, x-axis, right? The x-axis by negative 90. And after I do that, x2 will be pointing in the same direction as x1 because we just were spinning that one. But my new y2 axis is going to be pointing out this way, and my z2 is straight up now because when I spun this guy, right, so I'm spinning this guy around x, which is pointing sideways, and I'm spinning it in this direction, right, then the z sort of pops up because the z1 sort of is coming, I'm not very good at drawing this, but the z1 is kind of moving upwards from here, right, because we're spinning. If you imagine this guy spinning like that, and you're holding it like I'm pinching it over here on the edge, then spinning this is kind of spinning this way, which makes the Z go up, if that makes sense. Please, please get some physical things so you can look at this and see what's going on in 3D. Okay, so now we have, it's not very clear here, but x2 is pointing off to the left, right? That's my, oops. That is my x2 pointing to the left in the same direction that x1 was pointing, because that's what we were spinning. y2 is pointing out of the screen towards me, and z2 is pointing up. So all of the axes of the two axes are pointing in the same. They're parallel to their corresponding axes in B, and now we just need to do that movement. So in 2, this is the direction of x off to the left, but really we need to move 8 directions in that way. So if we get our pen, we're going to definitely be doing a trans, right? And the trans we're going to be doing is, we're not moving leftwards, we're moving rightwards. And since the x2 axis is pointing to the left and we need to go that way, so the trans is going to be -8 units along the x2 axis, right? Because everything is relative. The y2 axis is the in-out axis, so that's this one. And that's pointing towards me out of the screen, but we need to go backwards. So that's going to be, and then we got -3. And then we have the z-axis for 2 is the up-down, and we need to go up by 1 unit. And in this case, it's the same direction. So we're going to go up 1. So that's our trans. So just to summarize, let's shrink this a little bit. If I summarize them from left to right neatly, we've got rot z -90, followed by rot x of -90, followed by a translate by -8, -3, 1. So theoretically, if we throw this into Mathematica, we should get exactly the same result as we did from the previous slide. Okay, so we were doing the same example, but in a slightly different way. So I'll call this matrix example 2b, and I'm going to say that equals, this time we did rot z by -pi/2. I almost wrote 90. Matrix multiplied by rot x of -90. Ooh, I did write pi/2. -pi/2. Matrix multiplied by trans -8, -3, 1. And we get some mystery matrix. And let's just see, does example 2a equal example 2b? Check it out. It's true. They're equal. So we computed example 2a by doing a trans and then a rotation about x, a rotation about y. Down here, look at that. We did a rotation about z, then a rotation about x, and multiplied it by the translation then, and we still got the same result. So this actually, if I take this guy and display it as a matrix, you'll be able to see that this matrix is indeed the same as the one we had above, right? I'm sure you're convinced, but if I say matrix form of example 2a, and then I do matrix form of example 2b, you can eyeball those and say, wow, they look the same. That's amazing. And just to show you, we can do it any old way we want. I'm doing the same problem again, but this time I said, hey, let's do a translation, then a rotation, then a translation, then a rotation, then a translation, just to be annoying and crazy. So let's see. Why don't we start by doing this in-out translation, right? Again, the whole point is we should get exactly the same result no matter what we do. So let's do this in-out, which in terms of the a-axis, which is where we're starting, is a positive movement in the z direction, right? Because z points into the screen and we want to go that way. So the first thing that I want to do, oops, shrink this a little bit now. The first thing that I want to do is I want to translate along the z-axis by 3. So that's 0, 0, 3. And so after we do that, our new intermediate axis that we'll call 1 will have moved 3 units sort of in this direction. So it'll be about there. It'll be its origin. And we will have x1 points up because we didn't rotate yet. Y1 points off to the right, and Z1 still points into the screen. And now let's do one rotation. Maybe I'll rotate about Y this time. So if I'm rotating about Y, I can align the Z axis, right? If I, so Y is pointing out, Y1 is pointing out to the right, right? So Y1 is pointing to the right. So if I grab this and spin, that spins this axis down and this axis up, right? Because remember, Z is pointing into the screen. So then what we get if I rotate is, again, it's just a 90-degree rotation. I didn't do anything interesting in this example. Oh, well. And if I point my thumb in this direction, my fingers curl in the way I want. So I want to rotate about Y by a positive 90 degrees. And that will give me Y2 will still be pointing in the same direction as Y1 was. But now, so there's Y2. But Z2 is going to be pointing up, and X2 is now going to be pointing out of the screen towards me. And now for fun, let's do another translation. Woohoo! Why don't we do the 8? So that's the side to side, which is now in the Y direction. And I'm realizing I've drawn this badly. I drew my X1 and Y1, or sorry, my 1 and 2 axes a little bit too high for this picture, but that's okay. So we're going to translate 8 over to the right now, and you just have to kind of imagine that if I'm just moving straight to the right, I am going to end up really kind of in the up-down direction. I'm actually still 1 below this. So so I want to move to the right by 8, which is in the Y direction. So I'm going to do a trans 0, 8, 0. And that puts me sort of really where it puts me, even though I am, what I'm doing is I'm just moving horizontally, all right? But because my drawing is so horrible, and I want to look at it, where is it relative to this guy, really it's going to sort of put my origin here so that then I can go up and down in the Z direction. So I'm really just moving to the right, but just imagine that frame 1 and frame 2 were sort of drawn a little bit down and left a bit. So I'm moving frame 2 over to the right to get frame 3, but it's just a translation. So Y3 points to the right, Z3 points up, and X3 points out. So now let's see, my Z axes align. So if I were to grab up here, I could rotate it so that the X and Y spin into place if I go by 90 degrees. If I stick my thumb pointing upwards, my fingers curl sort of this way, which means that since I want to go that way, I need to do a rotation about Z of negative 90 degrees. So I'm going to say my next move is a rot of Z of negative 90 degrees. And now the only thing, well, let's show you what frame 4 looks like. What color? We'll do blue. So now X4 is to the left, Y4 is pointing out, and Z4 is pointing up. And so now I just need to do this move up, which is in the Z4 direction by 1. So I'm going to do trans 0, 0, 1. That's a mess, but we're going to go into Mathematica and multiply all that out, and hopefully it will just work beautifully. And we'll find that all three of our equations are the same. So let's throw that mess into Mathematica. Let's call it example 2c is going to equal trans of 0, 0, 3, matrix multiplied by rot y of pi, pi over 2, because pi would be 180, right? Matrix multiplied by trans of 0, 8, 0, matrix multiplied by rot z of negative pi over 2, matrix multiplied by trans 0, 0, 1, and we get something, and let's see, example 2a, does that equal example 2c? Shift enter, true, woohoo, we did it, beautiful, huh? So we can pick any arbitrary way to compute that frame transformation from A to B. And no matter how we do it, as long as we do it correctly, we end up with the same transformation. So these homogeneous transformation things are kind of clever.